Hello, my name is Daniel Farrell. I am a staff member with DataStax, and we're going to try to cover the topic of Cassandra cluster cloning atop Kubernetes within 7 minutes or less. A lot of moving parts. Let's see if we can do this. On the screen right now are elements of a toolkit I had showed before, a toolkit I created, just a throwaway toolkit for a benchmark I was on. So many of the steps run over and over and over again that you put them in scripts so that you're not typing commands repetitively. That sequence of steps will delete the Kubernetes cluster, recreate the Kubernetes cluster, provision the DataStax Cassandra Kubernetes operator using Helm, make a Cassandra cluster, and put a table and some rows of data in the Cassandra cluster, which that forms our starting point. That's our point of reference. We have a single Cassandra cluster, 3 nodes with data in it, and we want to clone it when working within Kubernetes. What's the use case for that? Dev and QA. You get a Cassandra cluster with some amount of complexity to the data, volume as data, you use it for unit and system tests, and you want to clone it over and over and over again to reset between these tests. There are some challenges to doing that in pure Kubernetes, Kubernetes version 118 and lower. And so I created this number of 5 or so slides to just show you graphically what we're trying to accomplish. So within Kubernetes are persistent volumes, and those are Kubernetes clustered-wide resources. An application, however, doesn't interact directly with a physical persistent volume. We use persistent volume claims. So persistent volumes could be created and stored in a number of ways. The application uses a claim. It's like a mount on a hard disk. A persistent volume claim is how the application hosted within Kubernetes interacts with the persistent volume. And where persistent volumes are cluster-wide, Kubernetes cluster-wide in scope, everything else we're discussing is scoped to a single namespace. There's no crossing between the boundaries of a Kubernetes namespace. It's one of the features of a namespace, so therein lies some challenges. So when we start a Cassandra cluster, as shown at the top of this screen, its PVCs and the Cassandra cluster are all scoped to a single namespace. And if we want to clone this across namespaces, we have a challenge. The first thing we need to do then using Kubernetes is to create a snapshot of the PVC. The snapshot is also scoped locally to a namespace. We could restore that snapshot back to its original location, but that's not what we're trying to accomplish here. What we're trying to do is create a second operating copy of something. So we create the snapshot, but it's locked to one namespace. What do you do with a snapshot? You can create a second PVC and an underlying persistent volume from that. The second PVC is how we cause a second persistent volume to be instantiated. But the second PVC, per limitations of Kubernetes 1.18 and below, is still in the original namespace, which is not our goal today. We want at least the persistent volume to be recognized by a persistent volume claim that is in, say, namespace 2. So the snapshot, the creation of that is asynchronous. We have to wait for that to complete. When we create a second PVC from that snapshot, based on your storage class, let's say it's a wait for first consumer, the PVC will exist and the PV associated with that will exist, but there's really no bits in the second PV. And so how we cause the snapshot to actually push its bits down to the second PV is we force a pod. We don't really need the pod. We need the effect of the pod. We force a pod against the second PVC. That'll push the bits from the snapshot down to the PV. And then we do a little bit of cleanup. We don't need the pod. We don't need PVC2. We don't actually even need the snapshot anymore, unless we're going to clone it a second, third, and fourth time. And now that we have the bits from the snapshot in PV2, problem solved. Now we can make the actual PVC we want available for a Cassandra second Cassandra cloned cluster in the proper namespace. The PV it references is cluster-wide, but the new PVC is in the proper namespace. We have a program for all of this, It's much less complicated than it sounds. So let's now look at the program. The program is about 600 lines. We could have written it in a number of host languages. Because we're on a benchmark and it's fast and down and dirty, we did it in shell script. Before we run the program, let's sort of look at the state of the state. So we have an operating Cassandra cluster. The Cassandra cluster could be up or down. It doesn't matter if we're going to clone it. 3 Cassandra nodes having a one-to-one relationship with 3 Kubernetes pods. Each Kubernetes pod has 2 containers. One of the containers per pod is Cassandra proper, everything you would expect Cassandra to be. And the second container per pod is really just the message log file. It's a means to tail the ASCII text file associated with each Cassandra node so you can see what's going on there. Here we see the pods in the first namespace, ns-cas-sys1. That's going to be our source Cassandra cluster that we copy from. If we move to the destination namespace, ns-cas-sys2, there's nothing in it from a pod standpoint. If we look at the persistent volumes, we see 3, 1 per node or pod of the Cassandra cluster. And just to finish out the PVCs then, notice that the PVs are named per the associated PVC. Looking at the PVCs, we have 3 in the source namespace, and we have 0 in the destination namespace. So let's run the program. It's got 8 logical steps. Some are faster than others. You can pass a command line argument, which is what should the destination namespace be for creating this clone Cassandra cluster, or it'll default to ns-cas-sys2. First, we flush each of the nodes in the Cassandra cluster, just in case we need to do that. Then we will check the target namespace. If you had previously run this program, you have a Cassandra cluster there. Possibly we delete all of that and wipe it. This is just for development, so I'm not worried about deleting anything of any significance. Step 3, because we're going to be using Kubernetes volume snapshots, we need a volume snapshot class, so we create that. Everything is created from the YAML. Step 4, we delete any previously existing volume snapshots, just some cleanliness to that step. It wasn't required. And then step 5, finally. So remember our graphics of earlier. We call to make a snapshot, 1 snapshot per each of the PVCs in our source Cassandra cluster. Making snapshots, like many things in Kubernetes, is an asynchronous operation. So we keep running the described volume snapshots with detail, and we look for a state of ready true. We're asking for 3 snapshots, so we wait for the report of 3 ready trues before we move forward. We need these snapshots to be complete before we're going to do any work with them. Making these snapshots takes a moment of time. We could be talking about hundreds of gigabytes of data, so it takes what it takes, but relatively it's generally very fast. Step 5 completes when all of the snapshots are actually ready. Step 6 then is one of 2 of the more complicated steps. So remember, we have the snapshot. We can make new PVCs from it, but only within the same namespace. And why are we doing this? It's a limitation of Kubernetes 118 or lower. We make the PVC not because we want a PVC, we make the PVC in the same namespace because we want it to create a persistent volume. Where PVCs are namespace in scope, persistent volumes are cluster-wide in scope. So really, we restore the snapshot to a PVC we don't want to force it to create the PV under the covers. But just like many of the operations in Kubernetes are asynchronous, the storage class we're using specifies wait for first consumer. So even though we have a PVC, the PV underneath it does not actually contain the bits from the snapshot. It won't until somebody claims the PVC. How do we force somebody to claim the PVC if we're not ready yet? It's in the wrong namespace. We make a little baby pod, a pod we don't actually want. So we have a PVC we don't want, we have a pod we don't want. We bring up these pods and they don't come up extremely quickly because the existence of these pods forces the PVCs to call to have the persistent volumes populated. Again, copying hundreds of gigabytes of data if necessary. Once these pods are up, we're ready for some cleanup and for some final assembly. Once these pods are up, the PV underlying it, the second PV, the copy of the PV, does contain the bits from the snapshot. We can kill the pods. We're done with them. After we kill the pods, we're ready for final assembly, step 7. And what is step 7? So we have the PV, the second PV, the cloned PV. We delete the PVC which caused it. Remember that PVC is in the wrong source namespace. Make that PVC go away. Just an additional step, that PV will show up as bound, so we have to free it, we have to make it available. Once the PV is available, now we can finally make the PVC, the final PVC, in the proper destination namespace. At that point, we're ready to boot Cassandra. I'm being excessively verbose here. It's really not as complicated as I might be making it sound. And as many things in Kubernetes are synchronous, just booting Cassandra means pods have to come up. Pods go through multiple states, initialization and other, in order for Cassandra to actually be up and running. So that's how you clone a Cassandra cluster within one Kubernetes cluster. We have all of this code and documentation and comments and error checking in a single file in this toolkit. It's file 58. You can actually even clone Cassandra clusters across Kubernetes clusters, but you're not going to do it with just pure Kubernetes 1.18 out of the box. There's many projects that will support that. The first one I fell into is from a VMware acquisition that they've since open sourced. It's on GitHub. It's called Velero, and you can easily clone across Kubernetes clusters. Velero basically gives us access to block storage. Copy it out of one Kubernetes cluster and into the second. And after the Cassandra cluster is up and running in both cases, you should see all your tables and data from the source system. So I hope you found this to be of value. There's dozens of posts currently, people trying to figure out how to do this, and it's difficult. So many articles, people not knowing how to do it. And at the end of the day, the steps are really not that complex. So again, hopefully you found this useful, and I will see you at the next video, at the next article. Thank you for watching.